In this video, we're going to be talking about the difference between vector quantities and scalar quantities. This topic, like in all honesty, is, like in my opinion, one of the most important things you need to understand to progress in physics, whether that be high school, university, or even if like you're studying for fun, whoever does that. Understanding these two is one of the like greatest foundations you can create to like excel yourself in physics. Having a good foundation of these is like what might take you from just getting past this course or excelling and maybe even enjoying physics. So starting off with the basics, what is a quantity? A quantity is something that can be measured. Weight, distance, speed, they're all quantities, and we've all taken a measurement of some sort before, whether that be with a scale or a ruler, or if you look at your speedometer. Those are all measurements, those are all quantities. But what you might not have determined is whether the quantity you're measuring is a scalar quantity or a vector quantity. So scalar quantities are measurements that are taken without a direction. These quantities, like, they only have a number or magnitude associated with them. Some examples of scalars are weight, temperature, distance, and speed. And like you might be wondering, like the last two things I mentioned, like can they have a direction to them? Right? Like they can have a direction to them. That's correct. Uh, but in a way, like if you associate a direction to them, those quantities are no longer scalars. Um, they become speed becomes velocity, distance becomes displacement. Now, it doesn't work this way with anything. I can say weight is 80 kilograms, but the minute I say weight, I weigh 80 kilograms north or 80 kilograms left. The sentence doesn't make any sense. And same thing goes with temperature. I can say it's 23 degrees Celsius outside, but the minute I say it's 20 degrees north or 20 degrees down, the sentence does not make any sense anymore. So, scalar quantities are magnitudes with no, underlining the no, hard no, no direction. We can't associate a direction with these. And again, temperature, weight, or mass would be the correct term. Let's not talk about weight right now. Weight is something else. Ignore I said weight. We're talking about mass. Mass is another one. Mass, speed, and distance are all scalars. Now, let's talk about vectors. Let's go blue. Red pill, blue pill. Vectors. Vector quantities are measurements that have a magnitude and a direction. They have a magnitude. Oh, let's go back to white. Magnitude and, underlining the and a direction. And some examples of like vectors are like velocity, displacement. Again, different from speed and distance, very different. Speed has no direction, distance has no direction. Velocity and displacement do have a direction. And acceleration. All these quantities have a like direction associated with them. Velocity, I can't write well. Velocity, displacement, and acceleration are all examples of a vector quantity. If I say I'm moving 50 kilometers per hour, then like you can assume that I'm talking about a scalar because you don't know what direction I'm moving in. I haven't clarified what direction I'm moving in. But if I say I'm moving 50 kilometers per hour west or 50 kilometers per hour right, that scalar quantity of just 50 kilometers per hour becomes a vector quantity. I've now associated direction with it, which makes that speed a velocity. That speed just became a velocity. So how do we tell the difference between uh, vectors and scalars in an equation or a question, right? Both speed and velocity are represented by the letter v, and both distance and displacement are represented with the letter d. So how do I know if a question is asking me to use a vector or a scalar quantity? Uh, answer this is actually very simple. Say v, speed is actually also v, distance is d, displacement is also d. How do we tell if we see a v in an equation, right? How do we know if it's a velocity or if it's a speed? How do we know if it's a distance or a displacement? Uh, Again, very simple. You put an arrow on it, right there. Put an arrow on the d right there. Now, a v with an arrow is velocity. A v without an arrow is a speed. D without an arrow is a distance, and a d with an arrow is displacement. Let's move on to some examples that might give us a better understanding of what we're working with here. Let's erase that line. So example 1, we're gonna call this guy Guy. Guy moved 10 meters east, and then he moves 5 meters west. Don't know why he moved 5 meters west, but he did. So he moved this way 10 meters and then back that way 5 meters. In this question, for distance, we're just going to calculate the total distance, which is going to be 10 meters plus 5 meters. We're not going to associate a direction. We're just going to see what's the total distance he traveled. And remember to keep your units in the equations. It's very important you guys build a habit to keep your units in the equations, just because later on, like let's say you're solving a really complicated question and you don't know if you're right or if your answer isn't right. So the best way to like double check is to see if your units match up. In this case, they're both the same units, so we can add them. We have 15 meters. So our distance is going to be 15 meters. So that's the total distance you traveled. Now, how are we going to calculate displacement? We can't do the exact same thing because now we're associating direction. We can't just be like 10 plus 5 equals 15 meters because we're not just doing 10 plus 5 anymore. It's a displacement. We have to account for the directions. So let's look at a small graph right here. Let's make it a bit bigger. I'm not going to include the y because we're just working on the x-axis right now. And let's make the midpoint of this 0. So anything to the right of this graph is going to be a positive, right? Which means anything to the negative, to the back is going to be negative to the other side of the 0. So in this case, we can make east our positive. Our positive is east, and our west is our negative. So turning west into east, turning this unit into this, right? Turning this direction into this, we're just going to say it's 5 meters negative east, while this is 10 meters east. So what we're going to do is we're going to do 10 meters plus, we're still adding, negative 5 meters because we're doing negative 5 meters east. Negative 5 meters. And again, remember to keep your units in the equation. They are the same units, so we can add them. Positive plus a negative makes a negative, so we're just going to do 10 minus 5. And our n is 5 meters. That's our displacement. So, like, how could it be 5 meters, right? That makes absolutely no sense. In what world is this distance plus this distance 5 meters? In the world of vectors, this is the displacement, 5 meters. We have a positive number here. It's a positive, which means it's 5 meters east. We can write that down as well. East. That is technically the final answer, 5 meters east, because that is the like distance traveled basically. Like his position from here to here, the change in that position is 5 meters. It's not 15 meters. A 15-meter change in that position is going to end up way over here. A 5-meter change in position is going to be exactly right over here, which makes sense because he traveled 10 meters east and then 5 meters west. Hope you guys are understanding. Let's move on to the next example, which is going to be a bit cheekier. In this question, we have Guy again. And Guy is moving 10 meters east. And then he does something weird and moves 5 meters north, which makes no sense. That shouldn't be possible. How is he doing that? For the distance calculation, gotta put an arrow here. For the distance calculation, it's still going to be the same thing, 10 meters plus 5 meters. Because we aren't associating a direction. We can't associate a direction when we're counting a scalar value. So we have 15 meters again. But now how do we get the displacement? We can't just do negative east anymore because he's not traveling this way anymore. He's traveling up. That's not a negative. If we do a graph, the negative on the x-axis can't be the y. So how are we going to get the y? I'll let you guys think on it. And just pause the video here and see if you can, I don't know, try to solve it. And then after that, I'll help you work through it. So we're back. So if you couldn't figure it out, something familiar going on here. You guys probably learned about this earlier in other like math classes, but right here we're actually looking at a triangle. Let's change a different color, just make it a bit easier to see. We're actually looking at a triangle here, which is, might light some light bulbs in your head about what we're about to do next. Now what we're going to do is we're going to use the Pythagorean theorem. A squared plus b squared equals c squared. What we call this line and this line, like what we're going to actually call them, this 10 meters east is going to be the x component of our vector. And this 5 meters north is going to be our y component of the vector. So our x component, let's consider the x component as a and our y component as b. Okay. Our x component of the vector, when we put it in this equation, we'll just move c to the other side right here, equals a squared plus b squared, just so it'll make our equation cleaner once we actually solve it. So we're going to do a squared plus b squared to find the vector using our x component and y component. So let's get the equation down first, because that just looks a lot cooler. That's how physicists do it. We're going to make the equation first. We're not going to put our values in first because that's weird. C equals under root a squared plus b squared. For a squared, we're going to substitute our x component, which is 10 meters. And for b squared, we're going to substitute our y component, which is 5 meters. And we're going to square both of them in brackets. Be sure to square them in brackets. And notice how I'm aligning my equal signs. This right here, this is like premium swagger. This is like, if you do this, your math teacher is going to be like, whoa, this guy knows what he's doing. Or your physics teacher, they're going to be like in awe. Just always be sure to align your equal signs. It always looks a lot cooler. So from here, since c is still equal to this is still equal to c, next one's still going to be equal to c, we're not going to write it just because a good physicist is a lazy physicist. We are not going to write this. It's actually not the proper way to say it. Let's square these right here. And again, I am including my units just so it makes my equation, I can't draw an under root sign, just so it makes my equation make sense. So 10 meters squared in brackets, emphasis on the in brackets, squared is going to be 100 meters. And I'm going to square the meters as well because I am squaring the meters. We are not ignoring the units. 100 meters squared plus 5 squared is 25. Meter squared is just meters squared. Don't ignore the units. If I ignore the units, then the units won't add up and it won't make any sense. So then 100 meters squared plus 25 meters squared. It's going to be 125 meters squared. And if I didn't have a calculator, I'd write 5 under root 5 meters. But I do have a calculator, and you're going to need a calculator for most of this course, most of these lessons, um, especially when it comes to the next step. So C is equal to, let's calculate this real quick, 11.8 meters. 11.8 meters is our C. Oh, we got the displacement, 11.18, sorry, 18 meters, not 8 meters, 18 meters. Yay, we got the displacement, 11.18 meters. No, we didn't get the displacement because we don't have a direction. We have a direction here, but we don't have a direction here yet. And like, you can't just write, oh, it's 11.18 meters, like somewhere above the east, right? That's not specific. For physics, if you want to be a physicist, you need to be specific. You need to tell the author you need to tell the reader exactly what you're calculating and exactly what you calculated. You need to give a direction. But how are we going to get a direction here? We're going to do something that you guys may also recall from a math class that you may or may not have taken. Hopefully you did. We're going to consider this angle theta. This is going to be our angle, which we can use to determine the direction. So, SOHCAHTOA, easy way to remember it. Sine equals opposite over hypotenuse, cos equals adjacent over hypotenuse, tan equals opposite over adjacent. In this case, since we already measured the vector, we can use sine, we can use cos, but just to make things simpler, we're going to use tan. Tan theta equals opposite over adjacent. Now, page does not want to move down. There we go. Tan equals opposite over adjacent. So let's make our equation first instead of just slapping in the numbers. We're going to move tan to the other side. So we have theta equals tan inverse opposite over adjacent. So our y component over our x component, which is equal to tan 1 equals our y component was 5 meters, again including the units, over 10 meters. Now we're just doing division here, so we can cancel out the units because they divide each other out. And then our answer for here is going to be 26.57 degrees. Yay, we got our direction. Still looks incomplete because we did not get our direction. We just got the angle. This angle could be anywhere. It could be here, 26.57 degrees. It could be here, 26.57 degrees. Here, 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 here. It could be anywhere. At 26.57 degrees could be anywhere. We haven't defined it in a certain range yet. So I made this easy by just doing like compass coordinates, north, east, south, west. In this case, our angle is moving up off east. Up off east, right? It's moving that way. Now up is just gonna be north, right? So it's moving north of east. So what we're gonna do is 11.18. Oh my god, I forgot the units. Meters. Don't make that mistake. You're gonna lose marks. It's going up north off east. So we're gonna do north of east. And that is our final answer for the displacement. So at the end of the day, what did we learn? We learned that vectors, and so a simple way to explain it, vectors have arrows, while scalars, make this red pill and blue pill again. Scalars, vectors Scalars have no arrows. And I'm not pulling this arrow stuff like out of my ass, right? Arrows are genuinely like using arrows to visualize your problem is one of the biggest tips I can give you guys. Like I still use it to this day in third year astrophysics. Like you'll catch me like tweaking in a test, moving my fingers around, trying to figure out, like trying to visualize the problem I'm facing, trying to visualize the equation. Arrows are very important. You're not going to get marks cut off if you just put in your arrows. In fact, you're probably going to get marks for including arrows, for including vector diagrams, which is the diagrams that I've been making. Vector diagrams being like, oh, it's a point, or actually, let's do guy. He moved this way, and then he moved this way. That is a vector diagram. The arrows have to go from tail to tip to tail to tip. You can't do it like this. You can't do it like this. It doesn't make sense. You can't do tip and tip. You can't make tips touch. Pause. What? You can't make it happen. You have to do tail to tip, tail to tip, and that is technically it's not a vector diagram. It's gonna be more like this. It's more of a vector diagram. Um, but like when you're doing like position or what the equations we've been doing today, um, be sure to do tail to tip. That's what we did up here. So wants to scroll. That's what we did up here. We did tail to tip, tail to tip. Even here, we did tail to tip, tail to tip. If we did it differently, we would have a completely different question. If we didn't do tail to tip here, we would have this, which makes no sense. 10 meters east and then 5 meters west, we're not going to get an answer. We're not going to understand the question. If we did it differently here, if we did it like this, we're not going to get the answer right. We're not going to be able to visualize the question. So be sure to do tail to tip, tail to tip. It doesn't matter which way you do it. You can do it from here. If you go here, let's do a different color. Let's do green. Tail to tip. We end up in the same location. Be sure to make sure the arrows are tail to tip and use your arrows as much as you can in whichever question you can because they are honestly very helpful. And that's about it. That's our scalars and vectors done. Hope you guys understood and found this tutorial helpful. If you have any other questions, just leave a comment down below. And if you have any other questions, practice questions, just feel free to email me. I'll leave my email in the description. If you have any practice questions, I will try to get back to them. And if they're really good practice questions, I might even post them on YouTube Shorts or TikTok. Just, a quick walkthrough, just teaching you guys how to solve that question. But yeah, thanks for watching, and just like and subscribe. And again, any questions, just leave a comment below. Next lesson is probably gonna be on velocities, just simple velocity calculations, displacement calculations. Yeah, see you.